Hi, I'm Colin B. Whitaker, a fourth-year PhD candidate with the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory, and I'm here today to talk to you about electrosprays. Electrosprays work by feeding a conductive fluid to the tip of a needle. By biasing that needle to high voltage, they emit an energetic beam of charged particles which can be used to produce thrust in space. And they're particularly attractive in this respect because they can be made very compact as a result of their liquid propellant, and they avoid certain pernicious loss mechanisms endemic to plasma-based propulsion systems like Hall thrusters or gridded ion engines. Most excitingly, by aggregating emitters together, electrosprays could be scaled to the high power required to support human exploration of Mars or other planets. However, since individual emitters are microscopic, doing so requires many of them. As an illustration, a single emitter produces less than 1 micronewton of thrust, about the weight of just the leg of a mosquito. To match the thrust of something like the X3 Hall thruster, which produces about 5 newtons or 1 pound of force, you would need about 10 million individual electrosprays. This introduces a number of challenges. In particular, while it's possible to mass produce emitters through modern manufacturing techniques, it is difficult to maintain tolerances in fabrication and alignment at scale. Combined with the fact that there's still much we don't know about how these systems operate, trying to ensure a system performs efficiently and avoids failure modes like electrical arcs to the emitters is an ongoing problem. At the University of Michigan, we're working to help overcome these challenges. The first component in our strategy is leveraging robust design. That is, we may not be able to avoid that some emitters won't perform as intended, but by accounting for these errors during design, we can search for a system that still reliably meets its requirements. The next part of our approach is a reduced fidelity modeling framework using things like scaling laws. These types of models are calibrated from real experimental data, but still bake in physical intuition. By also implementing learning methodologies like Bayesian inference, we can rigorously account for those sources of uncertainty. For example, this figure is from a study we did trying to predict the current emitted by an electrospray array as a function of its operating voltage. We found that we were only able to reproduce the behavior observed in experiment when we accounted for variability in the geometry of individual emitters. And finally, we are exploring novel architectures that try to mitigate known failure modes. For example, propellant that gets sprayed downstream can accumulate on the thruster electrodes, as you can see in this photo. This propellant can cause an electrical short that damages or disables the thruster. Here, we implemented an electrode consisting of a thin metallic film, such that when one of these shorts occurs, the film is ablated and the short removed. You can see in the photo that the metallization has been successfully eaten away where the propellant accumulated, a positive result for this prototype. Altogether, we're very excited about this research and look forward to sharing more about it with you as it progresses. Thanks for listening, and I encourage you to check out our website and the other videos on our YouTube channel to learn more about all the fantastic research at PEPL.